professor at MIT and the Sloan School and the Operations Research Center. He received his Ph.D. from MIT. I think he's the first MIT Ph.D. retired. He got his undergraduate degree from the National Technical University of Athens, and computer science. He really has a very broad set of interests. He works in stochastic systems, speed optimization, data mining. He works on applications in healthcare, health informatics now, revenue management, financial planning. I could go on a little further. He's written 3 books. The most recent is on speed optimization. He's about to finish a 4th book. He's received numerous awards. The most recent was just this weekend. He was inducted into the National Academy of Engineering. And while he was there, he met our president, Dan Moser, who most of you know received an award from the Academy this weekend as well. So we're very pleased to have you. And today we're talking about robust optimization.
Hello, very nice to be here. First visit to the campus. Seems a very vibrant society. Boy, you have lots of people with lots of interest. It's quite impressive. So I would like to tell you in the next 50 minutes, I understand, with my involvement with robust optimization. And there are some papers that were disclosed today. This is an area that I have been involved in the last few years. And if you happen to look at my website, you can actually download all of these papers. So the structure of the talk is as follows. I will try to give you some motivation, and then have a journey on robust optimization in various areas, from individual programming, to discrete optimization, of flows, conic optimization, and then linear quadratic control and inventory theory. Just to give you an idea that what I'm talking about, I feel, is applicable to many systems. So, what's the motivation? The motivation of this work is as follows. There are really 2 of them. First is that when we design systems or optimize, we typically assume certain values of some data. Let's say that we assume that some coefficient in the optimization model is 3.25. But in reality, it might not be that. So we find a solution X that assumes certain values of the data, but then in reality, the values of the data might be different. So therefore, the solution that we implemented might actually not be appropriate for that purpose. In fact, I was involved in some antenna design problem, and little changes in the data of the problem could make a huge difference on the quality of the solutions involved. So the question, therefore, that motivates part of the motivation is, can we design solution approaches that are immune to data uncertainty? That is, they are robust. The second motivation, which I think is quite important, is that if you look at the theory of stochastic optimization in the last 50 years, it is fair to say that as we try to model problems of stochastic optimization using probability distributions, typically these problems, by and large, and there might be exceptions, explode when the dimension increases, and therefore are not amenable to tractable computational methods. Dynamic programming has this character. So I don't feel that we have a complete theory, and that's probably an understatement, of tractable approach to stochastic optimization. So this aims to be tractable, and hopes also to illustrate that in addition to being tractable, it gives high quality solutions. But that was the second motivation. So what are the aspirations? To develop an approach that addresses optimization under uncertainty that has the following characteristics. First, it inherits the complexity of the underlying deterministic problem. So mathematical optimization is quite strong in that respect. In other words, we have developed over many years algorithms as well as software that, given a deterministic optimization problem, with all data deterministic, can really solve large-scale instances of this. Linear programming is perhaps the biggest success in this environment. So what we would like to do is to develop an approach that inherits the complexity of the underlying deterministic problem. So if the deterministic problem is efficiently solvable, then the new approach maintains, from a theoretical perspective, tractability, but also from a practical perspective as well. In addition, it allows the user to control the trade-off between robustness and optimality. Finally, something that is important is not only theoretical tractability, but also practical tractability as well. And I would like to illustrate. So, just as an overarching motivation, I'll tell you an application that I have been involved in financial planning. This was being, which is one of the initial motivators for myself to look into this area. I was involved in a financial planning system. So all of us have certain goals in life, right? We'd like to retire, we'd like to have our children going to, to appropriate schools, and then buy a house, and all of these things. The question is how we do it. So I was doing some work for American Express, the financial aspects of the company, and the question is to build such a system that using the web, advisors and clients of the company would actually utilize it to plan for all these things in a way that maximizes the probability of being successful. So the initial approach I have taken was using stochastic programming methods, and I'm afraid I wasn't able to solve it using lots of things that we weren't not. The problem simply exploded because we're planning financial advice for over 50 years. It's a multi-period problem with a lot of uncertainty, the principal uncertainty being the returns from the various assets involved. But what we have done is that we have taken this approach that I will detail in a second. But and I believe we have been successful, so much so that the company is now utilizing it as its key financial package for about 2.5 million clients, about 11,000 advisors, which means that we're able to do it using the web as interface. So as a result, the solution times were of the order of 1 to 2 minutes. So instant, but it wasn't overnight calculation. So this gives some credibility, I think, to the practicality aspect of this theory. I will return to this in the end of the talk. So just to fix ideas, I would like first to sort of introduce the approach with a stylized optimization model. And this is the following idea. So imagine an objective function, x is a set of decision variables, a vector in Rn, out of which some of the variables are integer, right? Not all of the variables, maybe none of them, but some of the variables may be integer, right? And you have linear constraints, and the variables are bounded. So this is an instance of what is called mixed integer optimization problem, in the sense, and from my experience, this is an eminently practical model. And some of the variables here, some of the data here, C and A in this case, are subject to uncertainty. In particular, the classical way of designing, of characterizing uncertainty is to define probability distributions. So instead, here's the model I'm going to use. This is one of many possible models, but I chose a simple one so that I believe I can communicate more easily the types of models. And it's the following model. Imagine a single row, let's say. There are uncertain numbers there, aij, and for every aij, we know a nominal value, aij, let's say 3, and then plus or minus, let's say 0.6. So there's some bound of where the data exists. And we also assume that for the purposes of proving theorems, not for the purposes of designing the approach, that the data is subject to an unknown probability distribution, but symmetric around the nominal value. In other words, the probability that you are, let's say, 3.3, let's say 3.2 is the nominal value, is the same as it is 3.1. That's a symmetric value. And similarly, there is uncertainty on the cost vector. There's a small value, there's a smaller Cj, and there's a discrepancy Cj plus Cj. So the true cost is in a certain interval. In addition, and that's an important point in the talk, is imagine the constraint. Let's say that the constraint involves 100 variables, there are 100 uncertain coefficients aij. Each of them in a certain interval. Imagine, though, that we want to say, okay, if 30 of them, the parameter chosen by us, change, I would like to find a solution that is feasible, that satisfies the constraint. If more than 30 move, I don't have deterministic guarantees, only probabilistic guarantees. In other words, I design, so this parameter gamma is a parameter that controls robustness. So if gamma, let's say, equals 0, it's a nominal problem. It allows no difference, no change in the data. So I'm prepared so that up to gamma changes, 0 changes occur, namely none. It's as if I solve a nominal problem. I assume basically everything is the average, and I go with that. On the other hand, if gamma equals the number of variables, I'm prepared for every eventuality. I would like to find a solution, but if everything moves, I'm feasible. On the other hand, as we realize, you go from the nominal to a completely robust solution. Gamma is a parameter that controls this trade-off. So speaking intuitively, it is unlikely that all the numbers will change. Moreover, it is even more unlikely that all the numbers will change in a truly worst-case setting. It's as if nature conspires to really maximally hurt you. So this gamma, in a way, is a parameter that tries to adjust to that. So we want to be protected against some changes, but not perhaps all of them. So this summarizes exactly what I said, that nature will be restricted its behavior in that only a subset of the coefficients will change in order to adversely affect the solution. So what is the problem that we would like to solve? So we would like to minimize Cx. This is the nominal. C is the nominal vector plus the maximum of dj. Dj is the variability. Fj subject to over all choices of changes up to the cardinality of the changes is less than gamma 0, and subject to the constraint that this is the nominal values plus the maximum over all choices of movements, if you like, up to cardinality gamma I should be less than pi. So in other words, I have the nominal value. So for example, if gamma equals 0, these terms do not exist. Right? It's just a nominal problem, which is basically what we have been doing in optimization all along. We were ignoring any kind of robustness. We're solving, the usual problems take the data in their values and go ahead and solve it. So this adds some robustness characteristics, right? So this is as far as feasibility is concerned, and this is as far as optimality is concerned. Any questions here? It's quite important that we are all together regarding what the model is. Yes?
So the DJ are
positive. They are positive.
So instead of putting across, it's hard to keep the x-rays small. How is that?
So let's say that we plan for, let's say that the C is 3, and it could be from 3 to 4, right? The Cj. One particular Cj is 3, and Dj is 1, right? So what it says is the following. The cost 3, I will pay, right? But the cost 1, I will only pay it if I choose the variable fj. If fj has a value, right? So I minimize over x, right? That's my decision. But nature or God will pick in a constrained way the true realization of cost in a way to help me within the constraint. It's a Minimax approach. Am I making sense? Yeah. So in a way, gammas are the parameters that choose that control the trade-off between robustness and optimality. On first glance, you should be wondering, what are you doing? You took a nice linear problem and you introduced nonlinearities here, right? So we introduce, maximization. It looks on the surface difficult, what I'm doing. It's not true though. So here's the first result. The details of this, forget it. The spirit is important. The first theorem is this. If the original problem is a mixed integer programming problem, the new problem is also a mixed integer using duality. If it's LP, linear programming, the new problem is also LP. In other words, it retains the character of the problem. Namely, the only integrality is in fact whatever original variables I had before, I still have them. And I introduce some new variables. So this is sort of the first objective, that I did not change the character of the problem. I introduced the uncertainty in this way, and I have a new problem that has some new variables. How many of those? Let's look at how many new variables. The details are not that important, you can see it in the paper. But what is interesting is this, that you have, let's say n equals 10,000 variables, and m equals, let's say, 5,000 constraints. It's a sizable problem, not gigantic, but sizable. So the new problem, the robust counterpart, has 2 times n, let's say 20,000 variables, plus 5 is 25,000 variables, plus L. L is the number of uncertain coefficients in the system. Let's say L is 2,000, we're talking about, 27, 28,000 out of 10,000. And then the number of variables, the number of constraints is the same. So you see that this is not a gigantic, it's an increase in the difficulty, the number of variables, the number of constraints, but it's not like a square. Like you have 10,000 variables and square, it makes it 10 to the 8, which is a very large number. You cannot pretty much solve it, or very difficult. So this preserves tractability. And something that is quite important from practical consideration is that optimization models are very much affected by sparsity. If you have a sparse model, you can solve. If you don't have a sparse model, typically you cannot solve it. Sparsity is preserved. In other words, the transformation is such that you add new variables, but the new problem becomes sparse. So in other words, what I would like you to remember from this is this, that here's a problem that has the robustness characteristic that when you transform it, it becomes equivalently a new problem where the number of variables increases, but in a tractable way, not in a... moreover, sparsity is preserved. LPs are mapped to LPs, mixed IPs are mapped to mixed IPs. So you have not changed the character of the problem. Oops. But notice so far I was completely deterministic, right? Probability played no difference. Everything was deterministic. I did not speak about probability, only in the very beginning. But now I'm going to use it. So obviously, because I have designed the solution, so no matter, so if nature behaves as I designed the problem, namely, if more than a certain number of changes occur, I'm fine, because I designed it. But the question is, what happens if more than, what happens if more than what I planned for change? So I would like you to focus on this. So the question is, suppose now there is a probability distribution. In other words, indeed, the data is changing according to the probability distribution, which is symmetric around the nominal value. Notice, because it is symmetric, it is equally likely that you are above the number and below the number. So there are cancellations involved. So the probability that you are, suppose you select your solution X star according to the robust problem I indicated by solving the new problem. So then the probability that you are infeasible is less than or equal, there's a formula here, but let's look at this, it's more insightful, I think. Phi is a cumulative zero standard normal distribution. So it's 1 minus phi of gamma minus 1 square root of n. So let's select gamma to be 3 times square root of n. Right? So let's say n is 10,000, square root of n is 100. 3 times 100 is 300. So this is 1 minus phi of 3, roughly. Phi of 3 is 10 to the minus 4. Right? It is 3 standard deviation. So if you select, in other words, if you have 10,000 variables, but you only protect for 300, the probability that you are infeasible, according to the symmetric distribution, is very, very small, 10 to the minus 4. So in other words, even though you only protected for only a relatively small number, 3 times square root of n, you are really probabilistically protected for much larger. Right? So and something that is interesting about this, that notice the exact distribution of the uncertain variables does not matter. I don't need knowledge of that. This is a universal bound. In addition, the only thing that matters is the number of variables. So let's say, therefore, how do I therefore select gamma? Here's how you do it. You say, I want the probability, so I'm a decision maker. And I say, I want my solution to be feasible with probability 10 to the minus 4. So I set it equal to 10 to the minus 4. I know, of course, what n is. I select gamma. Gamma will be, roughly speaking, some small constant, 2 or 3 times square root of n. So this is how I select my gamma. And notice, details of probability distribution are not important. They don't need it. They are not needed. Which I think makes it useful from practical perspective, because my own experience in the real applications is that very rarely we know anything about probability distribution. We don't. I mean, and the fact that it is symmetric, it is obviously something to do to make the results go through. But I don't think it's very unreasonable, because it's quite unlikely that you have data in a certain interval and you are the way, in other words, the data are coming are biased one way or the other. It might be on specific applications, but that's the assumption. You can also prove results with asymmetric distributions, but not as strong as this type. And this is an exact bound, this is an asymptotic bound, but really, typically it is quite an accurate bound. So to give you an example of the average here, suppose, in other words, you have so many uncertain coefficients. And suppose you are interested to pick the gamma so that the probability of the violation of this constraint is less than 1%. So you realize, well, if you only have 5 uncertain variables, there's not too much averaging going on, you better be fully robust. But as you increase the number of uncertain coefficients, you can get away with a relatively small number, the protection level is small. And why is this important? The reason that is important, obviously, the more you increase the robustness, the more you pay the optimality. So it is important that we don't overdo it with robustness because you will hit optimality. And I will illustrate an example to illustrate that point. In fact, right now, so this is a stylized example. This is not supposed to be a real application. It is just to illustrate the key idea here. Namely, that this is the so-called knapsack problem. You have some variable, n variables, each of them 0 or 1. You have one constraint and you have an objective. And let's assume, for the purpose of this discussion, that the costs are known deterministically, and the w's are within an interval. Right? wi minus delta I and wi plus delta I. And I pick some data to illustrate the point. I have 200 variables. Each wi is chosen in this simulation experiment to be 20, 21, or 29. And ci's are randomly distributed, and delta I is 0.1 wi. In other words, if wi is 20, the variable can be from 18 to 22. Right? So here's the fundamental trade-off. Suppose you pick gamma equals 0. Gamma equals 0 is the nominal. So in other words, you pay no attention to robustness, none. You just solve it the usual way. And you see that the probability of violation is 50%. So you have a high probability of violation simply because it can move you up and down from the constraint. Typically, at optimality, the constraint satisfies with the quality or close to the quality, so therefore the probability of violation is pretty high. And the optimal solution is 5592. Suppose you start increasing gamma, 3.8 and so on. You see that the probability of violation decreases, and if you pick gamma equals 200, it's 0. Obviously, right? Because you protect yourself no matter what happens. Because if you have a nuclear reactor, you protect yourself for everything. However, the objective function, notice that we are maximizing, so therefore the objective function decreases. This is a percent of optimality. So, if you are fully protected, so there's no possibility of violation, but you pay with 5.5% of optimality. On the other hand, in the middle, you pay much less. So so there is an advantage to pick smaller values of gamma because you pay with optimality much less. That's the key trade-off. Yes?
I'm sorry, are there uncertain coefficients?
C is known for the purpose of this example. Yeah, just to illustrate in a simple manner what is happening, the fundamental trade-off that we're having. And I would argue that depending on the application, different users might use different level of robustness. So depending on the series of the application, so one would argue that 10 to the minus 9 is really, for realistic purposes, more than enough guarantee. One would argue that 10 to the minus 3 would be reasonable guarantee and so on. But on the other hand, somebody says, I don't care about optimality, maybe I don't protect on anything. On the other hand, my own experience has been that in real world applications, I'll give you a story. Maybe I have a trade-off between stories and time of completion, but this is a realistic one. So I told you already one application on the financial planning. In the late 90s, I was involved in scheduling in a study to schedule the Panama Canal. The Panama Canal is a very complicated operation combining the two oceans. And in the year 2000, the Panamanian government became sort of the ownership of the canal. The American government went out, and the American government who started the study was quite worried that what will happen when they don't have control. I mean, a big portion of the world's big ships move through the canal, including a lot of ships with American flags. So we were drafted to build the system. So we built a sophisticated network flow problem. You know, we did bells and whistles and so on. We were quite proud of that. So we go to the canal, to Panama, and we had the presentation in front of the high-end people and so on. So we said we managed to increase throughput from 51 vessels a day to maybe 44 vessels a day. To increase throughput from 44 to 51, which is a fairly sizable number given that each ship contributes to $150,000 a day. That's a pretty sizable number on a government, on a small country like Panama. But the problem was, we presented it, we were quite proud. So somebody asked, what happens if there is one of the small vessels that is used to push this big ship breaks? Or some people get sick and don't show up when they say, I'm sorry, we didn't think of this. We were completely discredited. Even though we have, we're not, he was asking me, is your solution robust to changes? We're not prepared for that. We're not prepared for that. I will argue, of course, that it's not clear to me that they were doing robust to changes, but certainly ours wasn't. So that was a pretty interesting lesson in the story. That if they wouldn't, of course, they would care if your input, your throughput was increased, optimality was important, but was far less important than having a robust solution. And I've seen it many times that people are willing to give optimality if you have a solution that is more robust to changes. I don't know if you agree with your own experience, but this has been mine. So this is a practical view. Yes?
So in this combination, you only do distinction between small variations, large variations.
This is a very good point. In fact, in more recent work, I have been trying to address this. In other words, it might be a different story if you have, let's say, 1% violation versus 30% violation. But for the purpose of the talk, in the time, I have not addressed it in this talk. But we have something to say on that matter. It's a good point. So this is for the theoreticians of the audience. Might be some, but so typically my own experience. So when we started this work, this is one work with my former Ph.D. student LBC, I expected that robustness would change the complexity. The moment you add robustness to something, my expectation a priori was that it would make a polynomially solvable problem to make it an NP hard problem, difficult problem. And here's an example to examine. Suppose you have a combinatorial problem, like for instance the matching problem. You minimize the linear objective subject to x being a subset of 0, 1 vectors, and it is, let's say, a matching problem or a spanning tree problem or shortest path, some nicely solvable, efficiently solvable problem. And suppose, so x does not change, the problem is fixed, but the objective function changes. So for example, you would like the same kind of robustness, you would like to find an x such that up to gamma changes occur, you minimize the maximum deviation, the maximum of that. So my a priori thinking is that this is a hard problem. Let me tell you why. Here's a very similar notion of robustness. Suppose you have two objectives. Let's say you solve the shortest path problem, but you have two objectives. So one objective might be time, and the other objective might be distance. And you would like to find a solution you have to adjust the units that minimize the maximum of two objectives. That's a hard problem. Even though shortest path with one objective is an easy problem, shortest path with this robustness characteristic that you are good both in one objective and the other objective is a very hard problem. So this, in a way, was my motivation why I expect this problem was difficult. However, the particular way of forming the robust counterpart, and I have to admit, we did not, one thing that sometimes people make is that you invent the problem to prove the result. This was not the case. We first have done the work, applied it and so on, and then I was asking the question, maybe, what's the complexity when you apply for a fixed x, for a fixed combinatorial problem? And it turns out that something very unusual happens. So suppose you sorted the the variabilities. So d1 is larger than d2 is larger than dn. So what you do is you form n plus 1 possible objective functions. Again, the details are not the most, you will not understand them. But the key aspect is you form n plus one linear objective functions that involve the B's and the C's, right? So you solve, let's say, the shortest path problem subject to a linear objective function, but because you change L, right, you change the n plus 1 objective functions, you find n plus 1 solutions, and you take the smallest. This is the robust solution. So, which obviously suggests that if the original problem is solvable efficiently in polynomial time, the robust counterpart is also solvable in polynomial time. A rather rare property. It's a property that does not usually occur when you have robust guarantees, which illustrates that I think this model has some attraction. But doesn't illustrate that this in a way somewhat a result particularly appropriate for the particular way of randomness. Suppose you have another objective function. Suppose that your vector C, instead of being this, belongs in a certain polyhedron. So there's some uncertainty characterized by a certain polyhedron. Right? So then you minimize over X the maximum over C of Cx. That's an empirical problem. So in other words, it's not the case that any kind of robustness you add, it becomes easy. It's not. It remains easy. It is particular for the objective for the notion of robustness I have indicated. Right? So it's something to be careful about. So I don't want to create the impression that no matter what you do, you add robustness and suddenly you are fine. You have to be careful how you do it. So this is this result, namely that in the 0-1 case, the problem maintains its complexity. We did not change the complexity for this particular matter. Something similar also happens. Again, this is a continuation for the theoreticians in the room. Namely that, suppose the original problem is approximate to finite constant. Let's say it's guaranteed to be within the original problem, like for example the Tractable problem. We have guarantees about it under some assumptions. The robust counterpart of the Tractable problem would also have the same guarantee. So in other words, it preserves the good properties that we have developed for the nominal problem are transferred. Also a rare property. So approximation methods, if you change them, typically do not maintain the approximability, but in this particular case they do. So here's another problem. This is actually motivated by a practical application. The network flow applications are widely spread. So imagine you have a network flow problem, like for instance the shortest path or some other problem. And what's happening is the following. The moment, and let's say because C is subject to uncertainty. So it is from the previous results, you doing the robust counterpart becomes a linear programming problem. But the moment you take a network flow problem, you add new variables and constraints, you destroy the network structure. So you can still solve it efficiently in polynomial time, but as a linear programming problem. And for those of us who have solved problems, typically when you can solve problems as a network problem, typically it's about 100 times faster than solving as a linear programming problem. It makes a huge difference if problems are network versus not. That's why in many applications, I mean, it makes a difference being particularly real-time applications. Let's say you want automatic routing. Some of the cars nowadays have GPS and they compute the paths and so on. If it was a general linear programming problem, it would not have been done online, pretty much. So maintaining the character of the network structure is important. So what we have proven is that indeed, if you are careful with your analysis, you can basically solve the robust counterpart by solving a relatively small collection of network problems. You can either solve it as one big LP or iteratively solving a small collection of network flow problems, which makes it practical because it's logarithmic. So let's say you have 1,000, let's say you have 10 to the 6 variables, let's say, 1 million variables. And the number, let's say, is let's say 1,000, and have an accuracy epsilon. We are talking about 20 network flow problems as opposed to one bigger LP. And this is a worst case result, it's typically much better than that. So this was a study to see how robust methods could be applied for network flow problems and make it and design them in such a way that you don't slow them down too much. That was the idea of this. I will skip, given the time, some ideas that we have on continuous optimization, which I think is interesting. To illustrate, so far I have talked about the first motivation, namely, you have data, and the data changes, and you would like solutions that are immune to data. Right? That's what I've thought so far. So what I would like to talk about is something that is philosophically different from what I presented so far. Namely, so ask yourselves, why should we describe randomness as probability distributions? Of course, there's a very interesting theory, 300 years, and we have a nice calculus. But if you think about it, in applications, the primitive information is not distributions. I have yet to be in an application where someone tells me, and here's the distribution. Maybe you have, I have not seen it. So what I have seen is data. This is primitive. Somebody gives us some data, not distributions. It is our invention that we construct distributions through the data and then talk about stochastic models. That's typically my own experience, and I don't think it should be very different from yours. However, there are some issues with that, namely that from a complexity perspective, probability theory is somewhat unattractive. Suppose you want to find what is the probability that the sum of 10 random variables is less than 10, than 15. That's a hard computation. It involves multiple integrals and so on. It's not a piece of cake to do that. Probability is quite attractive in asymptotic theory, central limit theory, laws of large number. So you use asymptotics to make calculations. That's quite attractive. But the exact calculation, I would argue, is not particularly attractive. Related to that is the case of dimensionality. Dynamic programming typically explodes at the words of the founder of dynamic programming, Bellman. He used the word case of dimensionality. So therefore, this makes the following proposal. Instead of modeling randomness with probability distributions, model them with what I call uncertainty sets in the following way. And to illustrate, I would like to give you an example of one of the biggest successes of dynamic programming, namely inventory theory. You might not know inventory theory, some of you, but I think it's a very simple model. Well solved, by the way. This is not to prove that dynamic programming works very nicely in this case, but to illustrate the approach and the qualitative science that it gets. So this is a typical inventory problem. You have demand coming, and you order, and then the following day, the order comes, and you try to control it to minimize inventory costs. So this is a typical dynamic programming application where you have some state, xk, which is the stock available at the beginning of the k period. So the state is the stock available. The control, uk, is the stock ordered at the beginning of the k period. Randomness is the demand, which is typically modeled in a dynamic programming sense as a random variable. This is the key uncertainty. The dynamics are that the new state is the old inventory plus what you ordered minus the demand, and the cost is the ordering cost plus some convex nice cost. Right? So that's the typical model. I hope I didn't go too quickly about that, but this is not this is a well-known, easily understood dynamic programming problem. And there are nice results about it that I will illustrate. But before, let me try to model it according to the proposal I'm having. And the proposal I'm having is as follows. I'm going to say I have a nominal demand, Wk, and I have some variability, Wk hat. I'm going to say that Zk, the normalized demand, which is the Wk minus the nominal divided by the hats, is between, let's say, some numbers. And I also have an uncertainty value, namely, but I have, so if you think about it, if these are truly random variables, they do obey the laws of probability. So you would expect if you sum them, sort of laws of central limit theorem should hold. So instead of assuming the probability distributions, what I'm going to assume the consequence of probability theory deterministically. I'm going to say the sum of the deviations is less than gamma k, and I will pick the gamma k to control robustness and optimality. In a sense, I make a deterministic assumption of some of the consequences of probability theory. Right? That's the key result, that I'm taking probability theory and from a deterministic perspective. And if I do that, interesting things happen. First of all, because I can use the previous machinery, I take the problem, I write First of all, if the problem was completely deterministic, I could write deterministic recursions fairly simply. I add robustness using these constraints. I transform the problem to a problem in the same class. Let's say mixed integer program if the original was mixed integer, linear if the original was linear, and I solve it numerically. Right? So that's a problem that does not give rise to increasing complexity. But here's something interesting that happens. One of the key results of inventory theory-based dynamic programming is that the character of the policy is what's called base stock. This is for the experts in the audience that know something about inventory theory, but it's the following idea, that if the demand becomes lower than a threshold, then you order up to a bigger threshold. And what is interesting is that the same is true for the robust solution. So qualitatively, in other words, the solution has the same character than what you get through probability models. But what is particularly interesting is that you can compute these things using a mathematical programming problem. Of course, you say big deal. It's we could solve it before, so what? But there's a big advantage. Suppose you have a supply chain network, for example. Complicated networks, complicated structures, ordering, and so on. Nobody, to the best of my knowledge, nobody knows how to control a truly general topology network using general constructors with stochastic assumption of demand. That's, I think, a fair statement. This approach has something to say, because you write down a mixed IP, you formulate randomness using what I told you, you transform the problem using the general transformation that we have, and then we can solve it with mixed IP methods, which the software that can solve large scale. And you have the choice of picking the parameters, the gamma parameters, so that you can control the trade. What are you willing to give for robustness and optimality? You can control that. But most importantly, we can solve it. Here's another one, just to illustrate. One of the, I would say, arguably the most early, the biggest success of inventory theory in the early years was the Clark-Scarf model that says the following: you have inventory systems that are in sequence. The details are not greatly important, but if you ask to control these n inventories, there is a very nice closed form policy. It's a multi-dimensional problem, but because of its structure, dynamic programming has something to say. It's not easy to compute, but it has something to do with structure. What is interesting, if you apply the same thing using the robust approach, you get exactly the same policy in character, not the numbers, in character. And that illustrates that, it illustrates something to me that says that if the biggest advantage is to find the character of the solution, the character of the solution is maintained, plus you get numerical values that you can control from the using parameters, I think that's perhaps worth examining. So with this, this is just a stylized model, but it's a stylized model that basically says that you have a problem. But rather than modeling the uncertainties with probability distributions, you model it with uncertainty sets. You say they belong to a polyhedral P. And then the problem becomes, because I don't change the character, I think this is applicable elsewhere, not only in supply chains. And the major message here is that the numerical tractability is not affected by dimensionality, which is in some contract with the stochastic case. And in this particular case, we have insightful policies that are qualitatively the same nature with the stochastic case. In fact, they are close from the computer, unlike the stochastic case. So, and I know that some of my audience are in control, so I thought to tell you an application in control theory that I actually faced in an application. So here's the application, and then I will motivate it. So the application was as follows. So suppose you are managing money. You have Fidelity Investments, and Fidelity Investments decides on the manager of the fund is to trade, let's say, 1 million shares of IBM. If you go to the market and you sell 1 million shares of IBM, let's say the price is $100, you are not going to get $100. You are going to get a higher price. Because this price, your very nature of dumping shares in the market, a lot of it, if you buy 10 shares, nothing will happen. But if it's a lot, it will have a price impact. And you have to be careful how you schedule your trades. And this is not a minor effect, this is a major effect. So that's that's a major effect. That's why as the size of funds increase, typically performance suffers. They move the markets. It's like a big giant moving. So there's a way to model this using this formulation. Namely, that if you sell, let's say, you would like to decide how many shares to sell at this moment, 5 minutes later, and so on. So your decision is what to sell over the day. You have, let's say, a target to sell 1 million shares, and you have a cost that is typically quadratic in nature. That's a reasonable model. The problem is that the control, how many shares you sell at a particular time, is not a constraint in sign. By regulations, if you want to sell, you have to always sell. You cannot buy and then sell. So the number of UK, if you like, the number of shares you sell is positive. If it's positive in the beginning, it has to be positive throughout, right? Which is a problem if you apply linear quadratic control. Because linear quadratic control has great things to say. There are no constraints on the variables, but I would argue has very limited things to say if you have trivial control of the variables. So the mathematical calculation is follows. So, and you can forget now about the finance application. This is general purpose linear quadratic control. So you have some xk is the state, uk is the control, and you minimize the quadratic cost, subject to quadratic cost of the controls. You have linear dynamics, xk plus 1 is a vector, is some linear function of xk plus the linear function of the controls, plus c times the randomness, w is the randomness. So this is a problem, as stated, when you want to minimize the expected value of j, when the expected value is taken over the distribution of w, has a very nice clean solution that we teach in either control classes or in programming classes. And it's a Riccati equation solution. It's a beautiful equation, actually. The control is linear in the state, and you have a recursive mechanism of calculating the controls. Well, nice, implementable. I mean, I would argue it's the basis of the Kalman filtering kind of approach. That's a key component. So this is great, but suppose you have the initial constraint, uk should be non-negative. How do you do it? So I was faced with this. I had to solve this problem, how to sell, and I could not do it. The reason is, if you apply dynamic programming, you get an objective function that is piecewise quadratic with an exponential number of pieces. It blows up. You cannot do it. At least I cannot do it, and others. I have to compare. And so here's another approach. Forget about modeling with probability distributions. Let me model it. And this could be also other constraints. For example, I would like to control the probability that my state belongs to a certain targeted set, and with very low probability elsewhere. So dp is, I would argue, is not particularly robust in this. You change the assumptions a little bit, it does not work. So here's an approach. It's a similar approach. Model, forget about I need to change notation a little bit, but the key idea here is that I take all the vector of randomness, I put them in a big vector here. And instead of assuming probability distribution on that, I assume that some norm of W is bounded. So I take a Minimax approach, minimize over the U's, the controls, the maximum over W, where W is less than some gamma. I could pick other things here. I mean, the particular details of what set to take is not particularly important. But I could take, for example, this could be motivated if you have, let's say, normal, white noise. This is nicely related, mathematically speaking. I don't attempt to do it in the last few minutes, but with a quadratic norm. And for example, gamma equals 0 is the usual problem. But as we increase gamma, you have some robustness in the story. The nice thing about this is that you can model this problem as a semi-definite optimization problem. In other words, for those of you that do not know what semi-definite optimization is, it is a tractable convex problem for which in the last 10 years we have been able to solve relatively large-scale problems, tractable. What is nice about though is that the moment you start adding constraints, The semi-definite character does not change. It was semi-definite before, it's still semi-definite. So it is amenable to adding constraints, whereas the dynamic programming approach, it is not. And this, I think, makes a difference. What is also interesting, and this is some work with my current cases with David Brown of the engineer, is that even suppose you don't want to add constraints, suppose you really solve, this is your model and you would like to solve it. It turns out, instead of solving a Riccati equation and then online solve it, you have to compute L times X, namely a multiplication of a matrix times a vector. It's completely equivalent after some analysis using the robust approach with just solving one scalar nonlinear equation. So arguably, in other words, the online complexity and matrix multiplication times the vector is equivalent to, in the absence of constraints, with something that is of very similar order of complexity, namely solving by dissection a scalar equation, which I think is attractive from a computational perspective. But most importantly, this approach is amenable to extensions. You can add, for example, constraints on probabilities. You can add nonlinear constraints on variables, constraints on objective functions, and so on. And here's something else that in the part of the talk that I skipped. So semi-definite problem, I argue that it is computationally intractable, which is, I think, by and large correct. Except that semi-definite programming has a number of variables. So the unknown is actually a matrix X, which is n by n, is semi-definite. You see, X, let's say it's 1,000 by 1,000 semi-definite. We are talking about 1,000,000 variables. And symmetric, maybe 500,000 variables. That's a lot of variables. So we cannot really, this is, roughly speaking, the order where we can solve problems, about the dimension of 1,000, roughly speaking. In the work that I skipped in nonlinear optimization, we have actually found a method that is able to solve the same class of problems, second-order cone problems. The details for some of you are not perhaps not clear, but conic optimization, second-order cone problems are much closer to LPs. So in other words, from a practical perspective, so all are polynomial solvable, but there's polynomial and polynomial with a small p and a big P. So LP is sort of here. Second order cone is close, and then semi-definite is far away. And to illustrate that point, look at these numbers. So what I have done here is I took a problem and I started increasing the dimension. And I added constraints, the variables from negative and so on. The moment I am at 1,000, the dimension is 1,000, I cannot solve this problem, even with SDP. For the second order cone, I can solve it. And you see that there is a transition, but it's not night and day. I can solve this problem. So this is a part of the talk that I didn't fully talk, but the message here is this. It pays to simplify the problem in something that is easier to solve, like LPs, like second order cone, as opposed to using sort of the big machinery of semi-definite, which is very powerful and beautiful, but current technology, the current sort of optimization practice is limited. And the solutions are identical. So when you look at the solutions, this is not a typo. This table and this table are identical. This is the solution based on SDP and the solution based on second order cone. They are just the same. So, give you an example. So this basically says how different the solution is from the unconstrained case. If you use SDP, to 94%. The same is here. So what this means is that these two solutions are the same when they can be computed. It's not an artifact. So in summary, I'm robust in that respect. Right? So here's it was a journey on some application of robustness that we have seen that that we try to maintain the structure, mixed IDs maintain and are still mixed IDs of comparable size. LPs are LPs of comparable size. You have flexibility of adjusting the conservative level by this gamma. You maintain polynomial solvability on 0-1 problems, dynamical flow problems. And a key aspect aspect which I think is of interest is that, and I think this is sort of my major message. I have mentioned to you that a couple of years back, I have applied this approach to financial planning. And it was basically the following. I took the problem and said, suppose there's no randomness. So I formulated what was a mixed IP because there are taxes involved. It's a complicated problem, but doable. Using a language that fits in the programming, you can formulate the financial planning that involves, let's say, controlling of all your accounts, your taxable account, your education account for the children, your retirement account, your Roth IRA, and so on. But there are integer values. And then the way you describe randomness is by an uncertainty set. And now I can solve it because, perhaps when I model it, I take the robust counterpart, I double the variables, but I only double it. So, in fact, the requirement was that it has to be solved under 2 minutes through the web. This is how the financial advisors access it, which has been a success. In fact, American Express is now a new company called Bertsimas. There was a spin-off recently. But they are now using it for financial planning, and I expect there will be some ads to that effect in the near future in the public domain. And the other application I have recently been experimenting with is air traffic control. So this is the problem of controlling air traffic in the United States. Suppose there is a weather front that moves into an area and would like to reroute planes appropriately or call them in the ground. This is an area that Professor Boeing has worked quite successfully. But the question is, you would like to do it in the presence of uncertainty on the weather. Which is a critical uncertainty. How do you do that? I mean, to be honest, with stochastic programming, this model, even the deterministic model, is a large model. I mean, it involves approximately 1 million variables, which we can solve. I mean, we bought some computers at MIT recently. We can solve them. But, it's a computation that takes half an hour and so on, for a large model. Imagine now you're having, probability distributions on the weather. First of all, they don't exist. I can assure you of that because I spoke with meteorologists and I asked them, what's the probability of that? They look at me as if I was from another planet. So they don't have simple probability distributions on various scenarios. So the way we model it is to uncertainty sets. Same idea, basically extending some earlier work that I involved some years ago. And it still can solve it. Maybe it takes 2 hours and so on. So therefore, more work is needed. But we are in the ballpark. So in other words, we can do something about this. And I'm hopeful, although the research is ongoing, that this would actually be applicable, at least being able to solve technically the problem, whether it be applicable. The real application involves the complicated world of distributed decision making, which I'm not extraordinarily knowledgeable about in this particular case, in other areas I'm not mentioned. So thank you for your attention. I'm glad to entertain questions.
Time for 1 or 2 questions, but we got to make a meeting to
In fact, Ronnie Bertal is using it is related. In fact, this was part of the talk that I did not present because I had tons of things. But the area, just to be on the appropriate side, Professor Computational Ronnie Bertal and Katy Dimitris has used in continuous optimization settings, robust optimization in the mid-90s. So, with nice results and so on. The practicality, of course, because many of the problems were SVPs and so on. SVP is a hard computational thing, but they have done beautiful, nice work. And this is sort of in the same realm. They did not look into individual drivers. They are continuous optimizing. Ronnie Bertal is visiting me at MIT. We have lots of interesting discussions these days. The door next month.